Hi, welcome back. We will be going into chapter 13.5, textbook page 138. Yeah, okay, textbook page 138. It's on equation of motions, normal and tangential coordinates. So the objective of the lesson would be, at the end of the day, students will be able to apply the equation of motion with normal and tangential coordinate. Okay, so now before that, do you remember what I told you in the previous class? That when you have a curvilinear movement, yeah, you have a acceleration, right? You have a normal acceleration, which is going inward, and then you have a tangential acceleration, which is going, which is perpendicular to the path itself. Yeah. So this is where we are actually heading to. So if you see the title, it is tangential and normal coordinates. Yeah, okay. So example, any object that is actually going through a curvilinear movement, yeah, curvilinear movement, either on a flat surface, okay, either on a flat surface or on a inclined surface. So there are forces that will be exposed, or we can actually study the forces that is that is available on the object itself. Yeah, okay. So example, for this example here, racetrack turns are often banked to reduce the frictional forces required to keep the cars from sliding up to the outer rail at high speed. So that's the reason why this thing is actually banked or inclined. Yeah, inclined. So the cars will be actually inclined to keep the cars from sliding from the rail. Yeah, because you are actually traveling at a very high speed. The moment when you're traveling at a high speed, this is top view, when you're looking at the car from the top view. When a high speed taking a bend, it can actually get skid off from the track. Yeah, it is not that easy to keep it on the track. That's why you see, when you're driving on a rainy day, always advise that when you are making a path, a curvilinear path, you should actually slow down your car, because the car tires is the one that's helping the car to actually keep on the track. Yeah, okay. So if the car's maximum velocity and minimum coefficient friction between the tires and the track are specified, how can we define the minimum banking angle? So we're going to solve a question on this as well later. Yeah, another application is actually in the amusement park. Okay, like this object here, the hydraulically powered arms turns at a constant rate. Okay, I still remember this ride. I went on top of it when I was second year university. Oh god, the whole system was actually damaged the moment I got down. Yeah, headache, vomiting, and all this thing. But it's fun. So do it when you are still young. Okay, another park rides are those with a roller coaster. Yeah, they also undergo through curvilinear and tangential motion. Okay, so at the end of this lesson, you will be able to calculate all this. Yeah. Okay, so the applications, also satellites. Yeah? Satellites is also rotating around the orbit, around the Earth. So yeah, there is tangential velocity and also centripetal acceleration that's actually happening. Yeah, keeping it on the track itself. Of course, there's also gravitational pull. Yeah, gravitational pull, which is actually your centripetal force, the inward acceleration towards the Earth. Yeah, okay. So let's go into the lesson. So what do we have here? When a particle moves along the curved path, it's more convenient to write the equation of motion of normal and tangential coordinates. So normal is always points towards the path center, to the curvature. Okay, can you see this? Yeah, this is a normal. Yeah, whereas the tangential is always 90 degrees to the path. Yeah, 90 degrees, always tangent. Yeah, okay. Now we have another one. Let's look at this, because now we're dealing with 3D, isn't it? Yeah? This is something common you have exposed to. This is also okay. Now what is this new stuff here? Okay, now let's say okay, these blue ones, it's going to be a bit difficult for me to explain, just concentrate. Yeah, this blue one, you can see these two forces. You can see if your eyes is on top, it means you have an object and your eyes is top view. Sorry, I can't draw the top view. Yeah, so you can see the tangential and the normal. But let's say if this is the road, yeah, and your eyes is actually looking from the side view, side view, okay, so when you're looking at the side view, you can't see the tangential, but you can see the centripetal, the normal force, and also the contact force. Oops, oh, it went missing. Okay, no man, I'll redraw it. Okay, I'm actually explaining this. Yeah, I'm explaining this. What is this? This is the third axis. This third axis is, if let's say you have a car, yeah, you're looking from the road, the side of from the cross section of the road itself. So when you have a car, you have a contact force, right, moving upward, and then you have a centripetal force. You can't see the tangential force because the eye location is on along the tangential force. Yeah, so this is your centripetal and your contact force, which is the B. So this is something new. Yeah, it's called the binormal direction. Okay, so binormal direction. So it all depends on where is your eyes being placed. If your eyes is being placed on top, from the top, then you only see these two force exposed. But if let's say your eyes is from this direction, the tangential direction, so you're looking from here, then you cannot see this. Yeah, you cannot see this. You can only see the normal and the binormal force. Okay, so this is something totally new. Yeah, binormal force is totally new. You have not been exposed to it. So I hope you can understand. If you still don't understand, you meet me during the consultation hours. Yeah, so I can just demo to you. Okay. Okay. Now, FT and MAT. So this is the total force of tangential force and normal force. Yeah, along the same axis. Okay, let's move on. Okay, remember this? Yeah, radius or curvature. Okay, this only happens for cases which is not a perfect square. So if it's a perfect square, you see radius is the same all throughout. Radius is the same value. It's a fixed value. Okay, but then if you, let's say you have a curvy road, or you have a roller coaster ride which is curvy, okay, it has a radius, but the radius is keep on changing, right? So that's why the reason that we don't call radius, but we call it as a rho is called as radius of curvature. Yeah, radius of curvature, and looks very complicated, but it's actually not too complicated. Yeah, okay, I've actually explained to you in the last class also. It's not that difficult to solve this question. So the normal acceleration will be an v square over rho, and the tangential will be dv dt. Okay, okay, that part is done. Okay, solving problems. So the first thing is you define the coordinate. You know where is it. Yeah, you establish the coordinate. Then you draw the free body diagram. Of course, you need to draw the kinetic diagram. You need to show. Yeah, so there are two diagrams that you need to draw. Please do not forget. Otherwise, you lose marks in the exam. Then you apply all the equation motions that's applicable. Then you can write the relationship. So we will see this when we are solving a question. Yeah. Okay, like as usual, I'm going to skip that example from the lecture note. You can just go through it by yourself. Yeah, do extra reading because the examples are rather easy. So that's the reason why I'm going to skip this. I'm going to go to a textbook example, which is on page 140 textbook. Example 13.6. Yeah, okay, so at the end of this video, there are questions for you to solve. Just follow the study guide. Okay, so I'll take you to the example. So this is the example. So let's look at the example. Determine banking angle for the racetrack so that the wheels of the racetrack shown in figure 13.2 will not have to depend upon the friction to prevent the cars from sliding up and down the track. Assume the cars have negligible size and a mass and travel around the curvature radius rho with a constant speed of v. Okay. Now, look, your eyes is actually from the front view, cross-section of the car. Can you see? This is what I was trying to say. So when you see in that position, your eyes is placed in that position, you only see B and you only see N, normal. Yeah, the binormal force and the normal force. Yeah, you can't see the tangential force. Okay, so but then it's okay. We can just solve based on this, because what is the question actually asking? Question is asking, one second. Okay, assume the car track will not depend curve. Okay, assume car track have negligible size. Okay, determine the banking angle. Okay, so they want the banking angle. So the first thing to do is what? To draw your free body diagram. So how does your free body diagram look? So this is your free body diagram. Yeah, this is your free body diagram. And what is your kinetic diagram? So they have drawn a very simple thing just to show the arrow. Yeah, so this is the kinetic diagram. Okay, so what we have here? We have two axes, the n-axis and the b-axis. So what are the forces that is in the n-axis? We have the NC. This force can be actually resolved it to this line and also vertical line, right? Yeah. So the horizontal line will be NC sine theta. And it will be the mass AN will be V square over rho. Okay. You can't solve it, just leave it as it is. And then the FB. So what are the forces that is along the FB axis? So what we have here? NC cos theta, which is vertical from this component, and the weight which is pointing down. And of course, when you refer to the kinetic diagram, there is no movement. There is no movement in B direction. Yeah. If there is a movement in B direction, then the car will be moving up and down. So that is the meaning of movement in B direction. So of course there is no movement. It is only the normal movement. Okay. So that's why it's 0. Now if you combine these two, 1 and 2, yeah, you combine 1 and 2 because what do you call? Sine over cos. Yeah, sine. Okay, in this case, let me just show a bit of example here. So NC sine theta equals to mb square over rho. Okay, you divide by, so it is like 1 divided by 2. Yeah, so we have NC cos theta. You bring the minus g the other side, yeah, equals to mg. So when you divide 1 over 2, this m and m gets cancelled off, NC and NC gets cancelled off. So what we have here? We have sine over cos, which is tangent. Okay, and then we have v square divided by rho g. Okay, yeah, because when it's down and down, it gets combined. Yeah, okay. So settle. So this is how you find your banking angle. Okay, this is a bit, it's no numerical values here, it's algebra to solve this question. But anyway, it is tougher than numerical actually. So you have any problem, you just meet me during the consultation hours. So this is the end of this chapter. Yeah, you don't have to go through chapter 13.6 onwards. Yeah, this is the end of the chapter. Yeah, cylindrical coordinate, you can just study by yourself. Thank you.